All right. Before I look at your answers, I'm going to actually draw the Lewis structures for you. Oh, I forgot all the. Okay, I think it starts with CO2. Okay, that's okay. All right. So first of all, CO2. CO2. So we have carbon in the middle, oxygen, and then it should look something like this. And then we had CH2O. Again, carbon has the highest bonding capacity, so it should be in the center. And then we have oxygen, and then hydrogen's bonded to it like this. Okay. And then we had, I believe, SO2. Okay. So in SO2, sulfur brings 6 electrons, oxygen brings 6, but you had two of them, so altogether 12. We have 18 electrons, meaning 9 electron pairs. So sulfur in the middle. Why? Even though they both have the same bonding capacity or normal bonding capacity, sulfur is larger, okay? Therefore, it goes in the center. So please remember that. If two atoms have the same bonding capacity, then the larger atom goes in the center. How do we know sulfur is larger? Oxygen and sulfur are in the same group, but sulfur is below oxygen. Therefore, sulfur must have more shells. Therefore, it should be larger, right? And then we have two oxygens bonded to it like this. And then if I distribute the 9 electron pairs, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 electron pairs. But right now I have octets on oxygens but not on sulfur. I have two options to delocalize or share electrons and lone pair electrons so that sulfur can have an octet as well. I can do this, option 1, or I can do this, option 2. So if I do option 1, I'm going to get the double bond on this side, like this. Or if I do option 2, then I'm going to get the double bond on the other side, like this. Okay, so we have two possible Lewis structures for the same chemical formula, meaning we have resonance here. So these are called resonance structures. We can do the hybrid as well if we want to. Hybrid will be in between these two. So it should look something like this. Each bond is, this bond is not a double bond, not a single bond, something in between. Therefore, we can indicate like this. And then same thing on the other side, right? So this should be my hybrid structure for SO2. All right, now it's not relevant to this, but I mean I drew that anyway because we are talking about it. All right, and after SO2, I believe we have CCl2CF2, CCl2F2. I'm sorry, F2. So that's a straightforward one. So we have carbon, and then we have two fluorines bonded to it, and then we have a chlorine and another chlorine, like that. Okay, and then we need to make sure that we have octets on each atom by indicating the lone pairs, because without that, our Lewis structure is incorrect. Okay, that is CCl2F2. And then after that, I think we had NH3, right? So nitrogen, hydrogen, the same plane, and then another hydrogen, and then another hydrogen going away from us into the plane like that. Okay, that should be NH3. Again, I'm drawing 3D molecules in a 2D plane. I'm not expecting you to be able to draw them. I mean, for the moment, if you can, it is amazing, right? But at least you should be able to recognize them when you see them. All right, that's the whole point of this exercise of me drawing the 3D structures on a 2D plane. All right, now lastly we had H2O. So for H2O we had the two oxygen hydrogen bonds on the same plane, and then we should have something like that. So these are our Lewis structures for the 6 molecules. Can I get them on the same one? Almost. I think we can. All right, here we go. All right, before we move on to counting electron domains, what questions, concerns, comments do we have? Anything? Any questions, concerns, comments? Okay, so we should all be able to draw Lewis structures. I mean, I cannot emphasize this enough. All right, drawing Lewis structures is really important. Okay, now Going back to the question at hand, it's about counting the electron domains. Just to remind us about what electron domains are. Again, electron domains are, where are they? Okay, we wrote electron domains as, here we go. Okay, so electron domain can be a lone pair, a single bond, a double bond, or a triple bond. All right, whenever we see them, we're going to circle them as an electron domain. All right, let's do it. Here we go. So around the carbon, which is the central atom, we have a double bond here, electron domain, a double bond here, electron domain. Therefore, we have two electron domains in CO2, right? So in CH2O2, here's a double bond, an electron domain. Here's a single bond. Here's another single bond. We have three electron domains in CH2O. In SO2, okay, I'm going to pick one of these Lewis structures here. All right, so we have a lone pair, which is an electron domain. We have a double bond and an electron domain. We have another single bond over here, electron domain. Therefore, we have three electron domains. Okay, and then CCl2F2, we have four single bonds. 1, 2, 3, 4. Four electron domains. NS3, 1, 2, 3, 4. A lone pair is an electron domain. A single bond is an electron domain. Therefore, again, we have four electron domains. And lastly, we have S2O. 1, 2, 3, 4 electron domains again. Here we go. So we just counted the electron domains in each of our molecules. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions at this point about counting electron domains? Okay. Yes, Alyssa, right? Yeah. Can I have the microphone with Alyssa, please? All right, you can throw it to me. Alyssa, go ahead.
I'm still not understanding it.
Wait.
Like, why are you counting the lone pairs on NH3?
As an electron domain?
Yeah.
It's an electron domain. It's not, it's a given.
So
for example,
if it's a,
when I see the phone, I say this is a phone.
yeah.
Okay, so just like that, when you say like like lone pair there, it's an electron domain.
Now, what about the other lone pairs from the others?
In NH3,
Yeah, like, so I know like NH3 has a lone pair, but what about CClF?
I mean here,
Like, yeah, why don't you count those lone?
because they are not around the central atom. In the question, they are asking around the central atom.
Oh, okay.
Yeah, it's about reading the question. Yeah. So if you read the question again, it says, how many electron domains do we have around the central atom?
Okay.
Yeah. 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 Wonderful. All right. So why does it matter? Thank you. I mean, to talk about the central atom, because that is what is determining the shape of the molecule. All right. Now, here's what I want you to do now. Now, I want you to think about electron domains as balloons. Okay? So, you go to a birthday party and you have a lot of balloons, all right? So, for example, if we take CO2, CO2 has two balloons attached to the central atom. So, it's like holding two balloons in one hand. What kind of a shape does that make? You know what? Write the answer on your whiteboard, all right? If you hold two balloons, how do they arrange? Okay, what kind of a shape do you see? Go ahead.
Two balloons side by side.
Two balloons. All right. So you want the two balloons to be far apart from each other, all right? So if we have two balloons like furthest apart from each other, I mean, what does it look like? Thank you. I mean, name it as well. You have two balloons in your hand, far apart from each other. Okay. All right. So how does it look like?
You want me to bring? Yes.
Two balloons.
Somewhat.
Okay.
Okay, not that good.
All right. So if you haven't done this before, you should go find balloons and do the same exercise. Okay. And you don't have sticks anymore. You have two balloons, you're holding them from the knots with your hand. All right.
It's not.
All right. Can I see your whiteboards, everybody? I want to see your whiteboards. Thank you. I see. William, can I see what you have? All right. You even named it. Okay. You don't have sticks. You don't have like any sticks attached to it. You have them in your hand, like two balloons in your hand, like this. Okay. All right. So, do you have something for me? Okay. Okay. So you don't have like those threads. Okay. Anyway. All right. Thank you. So,
At Miami.
well, what we get.
He's not asking any real questions.
By the way, you have access to this. All right. So think of these as balloons. If you have two balloons, okay. All right. And then if you hold them in same hand, they're going to arrange like this. Okay. And then yeah, it's a straight line, right? And what can we call this? This geometry is called anybody?
In there.
What can we call this geometry? Or shape? Something again? Yeah, thank you. It's a line or it's called linear. All right. This geometry is called linear. All right. All right. Number one. Let's do another one. Okay. Now let's increase the number of balloons. Please get rid of those sticks with your balloons. All right. No sticks, no threads holding the balloons. You just, have like, completely filled balloons in your hand. That's it. That's all you do. All right. Now let's hold 3 balloons instead of 2 balloons in the same hand. What kind of a shape does that make? Can you name that or can you draw that on your whiteboards? Go ahead. 3 balloons. What kind of a shape do you see? If you hold 3 balloons in your hand, I see, thank you, triangle, right? It's gonna be, it's gonna make a shape of a triangle. And not only that, that triangle will be on a plane. Okay. So it's gonna be in the same plane. Therefore, that triangle is called that shape is called trigonal planar geometry. Look at this. You have 3 electron domains. They're gonna arrange like a triangle. Not only that, they'll be in the same plane. All right. Therefore, it is known as trigonal planar geometry. All right. One last thing, then we're done. All right. Now, let's hold 4 balloons, not 3, 4 balloons. What kind of a shape do you see? Go ahead.
Yeah.
If you have 3 balloons, 4 balloons now, okay,
Tetra.
how would they arrange in space? You have, have the greatest separation between them. Go ahead.
Like it already has like so
What is that shape?
this side of this whole thing. Like for example, it's a rectangle. So rectangle is one side of this whole duster. But this whole thing is a duster. So it's like a keyboard. The same way that you draw it. It's like a pyramid. I don't know.
I think most of you drew them. Okay, look at that. Okay. So if you tell me that when you hold 4 balloons in your hand, they are going to arrange in a cross or a T, you need to go home and hold 4 balloons today. Okay? So they will not arrange in a cross or a T shape. Okay? So instead, they're going to arrange in like a cheerleader position, like their arms and legs far apart from each other like that. Okay? Why? Now, if you have a cross, the angle between them is just 90 degrees, right? But if you have like this cheerleader position like this, the angle between the balloons will be more than 90 degrees, like 109.5 degrees, okay? And that shape is known as, let me show you, right?
Oh,
Tetrahedral geometry. Right? The cool thing is the bond angle on the angle. No, it's not bond actually. Okay, the angle between the balloons will be much greater than 90. Okay, that's why they are arranged like that. Okay, so one thing to keep in mind: these electron domains are like negatively charged. Right? They repel each other. They want to be as far apart from each other as possible. Okay, that's why they're going to arrange like this to have like in the maximum distance between them. All right, so these are the three possible shapes you're going to have for the electron domains. Now what I want you to do is I want you to make a note of that in this question. Here we go. Here are the same molecules. I want you to determine the electron domain geometries or balloon geometries for these molecules. Go ahead. There are only three possibilities, right? Linear, okay, trigonal-planar, tetrahedral. That's it. Those are the only possibilities for
Tell what?
all right. We have more than 90% answers. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. Okay. CO2 linear, CH2O trigonal planar because we have 3. SO2 again trigonal planar. I don't know why that is going down.
I don't
Actually, I know a reason, but we'll get that later. CCl2F2 tetrahedral because we have 4 electron domains. NH3 is tetrahedral as well, and H2O is tetrahedral as well. Okay. Now, I kind of have an idea why it's kind of low for SO2 and H2O and NH3, but we'll get there later. But does anybody have any questions, concerns, comments at this point? Anything? Okay. By the way, people who's had something, for example, anybody who had H2O as bent, okay? Remember the question is asking about the electron domain geometry. Whenever we have 4 electron domains, okay, they're going to arrange in tetrahedral. Okay, tetrahedral geometry, not anything else. Okay, so if you had something like bent or trigonal pyramid or something like that, that's because you're a little bit ahead. You're thinking about molecular geometry. We're going to get there. Okay. All right. Now, let's do this. Yeah, I'll reopen this in case somebody wants to revise the answers. All right, I want to go back to this model. By the way, the simulator is available to you as well to play with. Okay, now let me show you something. So carbon dioxide, okay, looks like this. Okay, now all this time, only thing that we considered was the electron domain geometry, which is okay. But when it comes to the shape of the molecule, all right, I mean, we need to go a little bit beyond the electron domains because, not all the time electron domains in geometry matches with the molecular geometry. Okay. But for carbon dioxide, they match. Why? We see that our only 2 electron domains are bonding electron domains. Okay. Therefore, the molecular geometry and electron geometries are the same. So let me actually write something here so that you understand what I mean. Let's think about H2O for a minute, okay? In H2O, we have HO bonds, and then we have 2 lone pairs. So here, these sticks or these lines are called, okay, bonding electron domains. These are bonding electron domains. Okay. On the other hand, we have these lone pairs. Okay. These lone pairs are called simply lone pairs or lone pair electron domains. Okay. So what we are seeing is this, right? If we have number of electron domains here, like in for example in carbon dioxide it is 2, and then number of bonding electron domains, okay, which is going to be 2 for carbon dioxide again, right? And then lone pairs for carbon dioxide is 0, okay? So we know that our electron domain geometry, I'm going to write it like this, electron domain geometry, okay, is linear, okay? Because our 2 electron domains are bonding electron domains, okay, my molecular geometry is also linear. Molecular, listen, geometry is also linear. All right. One other thing, what would be the angle between the 2 bonds in carbon dioxide? Let me show you. Okay. What is this angle between the 2 bonds? Two double. What is that? Yeah, 180 degrees. It's a line, right? Okay. Therefore, the angle between the bonds is 180 degrees. So we can write that down as well. So the bond angle is 180 degrees. Okay. Now, let's switch to 3 for fun, okay? So if we have 3 electron domains, just like in CH2O, right? And all of my electron domains are bonding electron domains, lone pairs are 0, okay? We saw that our electron domain geometry is trigonal or trigonal planar, okay? Now, what can you tell me about the molecular geometry of CH2O? Anybody? What is the molecular geometry of CH2O? Let me show you what we are referring to. Okay, so we have, yeah, here's CH2O. Okay, what is the shape of the molecule here? Thank you, Tyler. I'm gonna come back. Yeah, William, thank you. Yeah, it's trigonal plane. It's like a triangle. Okay, and in the plane, right? Okay, because my electron domains are bonding electron domains, the molecular geometry is also trigonal planar. All right, so we can see a pattern here really soon. All right, because these are the same, my molecular geometry is also trigonal planar. All right, another question. What is the bond angle here between the bonds? Tyler, do you want to have a stab at it? What's the bond angle? You take a pie of pizza and you divide that into 3 slices, or you cut that into 3 slices. Okay, or you take 360 degrees and divide that by 3. What do you get? Thank you. It's 120 degrees. Right? So the bond angle here would be, actually this can actually show you as well. It's 120 degrees. Okay, 120 degrees. I'm going to do one other example and then I'll take any questions you might have. Okay, I'm going to show you a deviation from this trend now. Okay, so say that we have something like SO2. This guy over here. We have 3 electron domains. Only 2 of them are bonding and 1 of them are lone pairs. Okay, it's a lone pair. All right. So we have 3 electron domains. 2 of them are bonding electron domains, and 1 of them is a lone pair. Okay. Now, if this is the case, we know our electron domain geometry is still trigonal planar. Trigonal planar. Okay, we're talking about the 3 electron domains here. Okay, but the molecular geometry looks something like this. So here we go. So let me get rid of this. Oh no, it's too much. Okay, let's do this. It looks like this. It's like an alien, right? I don't know. I haven't seen an alien. Um, anyway, so yeah, I mean, it's kind of ruined it for us. So anyway, so what kind of a shape is this? It's not linear anymore, like in carbon dioxide. What can you call this shape? Anybody? Tyler, go ahead. Yeah, thank you. Okay, we're not going to get fancy here. It's not linear anymore, but it's like bent, right? So the molecular geometry is called bent. Okay, and remember when we're talking about the molecular geometry, we are not looking at the lone pair. We are hiding the lone pair and looking at the rest. Okay, it's like hiding the lone pair and then looking at the rest of the molecule, how the atoms are placed in the space. Okay, that's what we're looking at when it comes to molecular geometry. But when it comes to electron domain geometry, we are looking at where all the electron domains are placed in the space. Right? So let's make that note. Right? If we have 3 electron domains and only 2 of them are bonding and 1 of them are lone pairs, it's a lone pair, then we have a bent geometry. The molecular shape is bent. Okay. What about the bond angle? Anybody? Thank you. It's still again, the bond angle is dictated by the number of electron domains. All right. It's going to be 120. But here's the thing. The lone pairs tend to take up more space than bonding electron pairs, bonding electron domains. As a result of that, the bond angle will be a little bit pinched compared to 120 degrees. Therefore, bond angle is little bit less than 120 degrees. I'm going to use the less than sign in front of the 120 degrees to show it that it is less than 120 degrees. All right, one more thing. All right, 4 electron domains, and then all of them are bonding, 0 lone pairs. Okay, we know if we have 4, it's going to be tetrahedral electron domain geometry. Okay, what can you tell me about the molecular geometry based on this trend? Okay, all my electron domains are bonding electron domains. Therefore, the molecular geometry is also, thank you, Tyler, it's still tetrahedral, right? Okay, I heard the hands from here. It's tetrahedral. Okay, what about the bond angle? Angle between the bonds is, let me show you. Yeah, here's what we're looking at. What's the angle between the bonds? Anybody? Abby? So if it is like a cross, it would be 90. Yeah, it's more than 90 now. It's more than 90. Does anybody know the exact angle? Oh, perfect. Yes, sir. 109.5 degrees. Okay, yeah, it's a weird one, but whenever we have like tetrahedral geometry, the bond angle is 109.5 degrees. Okay, so let's make a note. Gonna be 109.5 degrees. All right, so I'm gonna keep going. So if you have 4 electron domains, but only 3 of them are bonding, and 1 of them is a lone pair, electron domain geometry must be what? Like in NS3, for example, NS3. What is the electron domain geometry? Everybody should know it now. What's the electron domain geometry of NS3? Thank you, tetrahedral. Why? Whenever we have 4 balloons, they're going to arrange in a tetrahedral geometry, right? So electron domain geometry is still tetrahedral. It's not going to change. It's dictated by the number of electron domains. And what about the shape of the molecule? Okay, so here's what we have. Instead of 1 bond here, we have a lone pair. It's like an alien ship now, right? Okay, so what can we call this this shape? Anybody? What is this shape? William? Yeah, thank you. It's called trigonal pyramidal. All right, it's like the alien ships we have in Egypt. No, those are pyramids. Anyway, so these are, yeah, this is called trigonal pyramidal geometry. All right, let's make a small note. Right, So the molecular geometry is trigonal pyramidal. Okay. Again, only thing we did was we hid the lone pair and then we were looking at the rest. All right. That's all we did there. So if you just hide the lone pair and look at the shape of where the atoms are placed, it looks like a pyramid. And also the face of the pyramid is like triangle. That's why they are called trigonal pyramidal molecular geometry. All right. And then let's do that. Okay. What about the bond angle? Anybody? Yeah, still 109.5 degrees, but because we have a lone pair, okay, this lone pair is going to pinch the bond angle a little bit. As a result of that, the bond angle will be less than 109.5 degrees. All right, one last thing. 4 electron domains, but only 2 of them are bonding and 2 of them are lone pairs, just like in water. Example is water. Okay. Okay, what about the electron domain geometry? Electron domain geometry is what? We have 4 electron domains. Therefore, the electron domain geometry is, thank you, tetrahedral. 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 All right. Now, the shape of the molecule, let's look at it. Right. So here's what we have. We have 2 lone pairs. Oh, look at that. It's a weird alien now. All right. Anyway, so what is the shape? If you forget about the lone pairs, if you just look at the atoms, what kind of a shape does it make? Yeah, again, it's bent, right? So this is no, it's already here. Anyway, it's called a bent geometry. And also the bond angle would be, what's the bond angle? Anybody? Bond angle must be, yeah, less than 109.5. Okay, less than 109.5 degrees. Right, this is it. So these are the only geometries that we need to know. Okay, this table, this half a page, summarizes everything that you need to know when it comes to geometries. All right. What questions, concerns, comments do we have at this moment? Anything? All right. So with that, all right, I'm going to close this discussion in 5, 4, 3, 2, and 1. Right? And then here are our responses. It's beautiful. All right. We are almost 90% in all of them. I think the lowest is NS3. See what's going on here. Okay. So again, NS3 is trigonal pyramidal. All right. So we have a tetrahedral electron domain geometry, but you have 4 electron domains. Only 3 of them are bonding. One of them is a lone pair. If that is the case, according to the chart we just made, it's going to be trigonal pyramidal. Right. So this is that, which is pretty good. Any questions, concerns, comments at this point? Right. So now, so during your exams and quizzes, I mean, quizzes is fine because you need to, you can use your notes. Okay. But when it comes to exam 3B, you need to be able to, imagine these shapes because you don't have access to a cheat sheet or something like that. Okay. Where you can have this, this chart. Therefore, you need to, think about these molecules, molecular shapes, when you try like homework problems and then, other discussion worksheets problems and stuff like that, so that you will remember it. Okay. Bless you. Again, when it comes to electron domains, it's very easy. There are only 3 shapes: linear, trigonal planar, and tetrahedral. That's it. All right. And then when it comes to molecular geometries, we can have linear because if we have like 2 electron domains and both of them are bonding, it's linear, right? And then it can be trigonal planar, 3 bonding electron domains with if you have 3 bonding electron domains and that's it, it's going to be linear. And then if you can have bent, okay, bent you can have when we have 3 electron domains and only 2 of them are bonding. If that is the case, it's going to be a bent geometry. And also, if you have a tetrahedral electron domain geometry and only 2 of them are bonding, then it's going to be bent as well, right? And then the other shape is tetrahedral, molecular geometry when you have 4 bonding electron domains. And then we have trigonal pyramidal, which is the last one. Okay, when you have 4 electron domains, only 3 of them are bonding, and one of them is the lone pair. Then it's going to arrange like a spaceship or a pyramid. Okay, that's going to be a trigonal pyramidal. That's it. Those are the only shapes that you need to be concerned with. All right. Any questions, concerns, comments at this point? Okay. So you can use the chart we made, but try to imagine, these shapes in your head when you're trying out these problems as well. And it's going to help you definitely with your exam 3B. Right? Okay. So with that, let's try this. Bond angles as well, just for fun.
Do it. EDG is electron domain geometry. MG is molecular geometry.
So again, please draw the Lewis structures on your whiteboards, on your notebook or somewhere. Okay. Do not cut. All right. So I just want to see your answers. I'll reopen this, but I want to see your answers now. Okay. All right. I'm going to close this question in 5, 4, 3, 2, and 1.
This. I was talking to a student.
All right. And here are our responses. All right. Oh, there's something wrong. I don't think this is the correct answer. I mean, this is not what you submitted. I don't think so. Bend. Okay. Anyway, I don't know. All right. Let's do this here.
Today something funny happened.
Papa is crazy sometimes. Okay. Anyway, so this is what we have. Start with SO3.
Calc exam right before this class.
Right.
I said
Sulfur brings us 6 electrons.
I was like in my bed.
Oxygen brings us 6 as well, but you have 3 of them. 3 times 6 is 18. Altogether, we have 24 electrons, meaning 12 electron pairs. Okay. So sulfur is larger, therefore sulfur is going to go in the middle. And to that, we have 1, 2, 3 oxygen atoms bonded. Right. So we have 12 electron pairs. I use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? And right now I have distributed my 12 electron pairs, but I have octets on oxygens, but not on sulfur. So what do? We delocalize this lone pair so that sulfur can have an octet too. Okay. So when we delocalize, so when we share these lone pairs, we have 3 options. We can do this. 1 or 2 or 3. Okay. So if you do 1, you're going to get the double bond on the top like this. Okay. And if we do option 2, then we are going to get the double bond on the side like this. Okay. Or if we do 3, then we are going to get the double bond on the side, on the right side like this. Okay. So in other words, we have 3 possible Lewis structures or 3 resonance structures for this. Therefore, SO3 shows resonance. And these are my resonance structures. Okay. So the actual structure is going to be a hybrid of all these. Therefore, this top bond is not going to be a double bond, not a single bond. It's going to be something in between. So it should look something like this. Okay. So same thing for all the other bonds as well. So here's the hybrid structure. Hybrid. Okay. So once again, around the central atom, we have 1, 2, 3 electron domains. You can pick either Lewis structure over here. Okay. 3 electron domains. Therefore, the electron domain geometry is trigonal planar. And all of these electron domains are bonding. Therefore, the molecular geometry is also trigonal planar. Okay. So EDG is trigonal planar. And then molecular geometry is also trigonal planar. All right. On the other hand, if we do SO3 2 minus, okay, do the same thing. Sulfur, we get 6 electrons. From 3 oxygens, we get 18 electrons. From the negative 2 charge, we're going to get 2 more electrons. So altogether, we have 26 electrons, meaning 13 electron pairs. Okay. Now again, sulfur should be in the middle. To that, we have 1, 2, 3 oxygens bonded. 1, 2, 3. Okay, I have 13 electron pairs. I use 3 of them. I'm going to distribute the others starting with oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the 13th one, the last pair, should go on sulfur. Okay. Now I have octets on all 3 oxygens. I have an octet on sulfur. This is it. This doesn't have resonance. So SO3 2 minus should have this Lewis structure. Then that's it. No resonance. Is somebody calling me? All right. I don't know. Nobody calls me. I don't know why. No. All right. Anyway, so these are our resonance, our Lewis structures. For SO3 2 minus, the electron domain geometry is tetrahedral. Tetrahedral. Why? We have 1, 2, 3, 4 electron domains around the central atom. And then the molecular geometry should be trigonal pyramidal. Trigonal pyramidal. How do we know? Whenever we have 4 electron domains, okay, and only 3 of them are bonding, one of them is lone pair, the molecular geometry is trigonal pyramidal. That's it. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Okay. I'll reopen the question, and then meanwhile, I'm going to do one last molecule here. All right. Now I'm going to give you a line structure, convert the line to Lewis, and then determine the bond angles. All right. These red arrows are asking for the bond angle. All right. All right. People are getting anxious. I don't know why. All right. So here's what we need to do. All right. I'll quickly close this question to see where you are at so that I get evidence of learning and then go back to this. Okay. I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are responses. I don't know what Topper is doing today, but anyway, but it's okay. All right, let's do this here. I'm going to reopen it. All right. So all you had to do here is to convert this to a Lewis structure, but not all of them either. Okay, just the atoms of concern, right? So here we have angle 3 is around this carbon atom over here. We have 3 bonds around it. We need to add a carbon-hydrogen bond to fulfill the common bonding pattern of carbon. Okay. Now we see that we have this. We have 3 electron domains around this carbon. All of them are bonding electron domains. Therefore, this should be trigonal planar electron and molecular geometry. And we know if we have that, this angle must be 120 degrees. Okay, that's number 1. And it's number 3 actually, I'm sorry. So number 1 over here is the carbon again. Bend is a carbon. We have 2 bonds. Therefore, I need to add 2 more carbon-hydrogen bonds. So it's a perfect tetrahedral geometry when it comes to molecular and electron domain. Therefore, we know it has to do with 109.5 degrees bond angle. So this bond angle must be 109.5 degrees. Okay. Same thing for angle 4. This is a carbon over here. We just need to add 1 more carbon-hydrogen bond to fulfill the common bonding pattern. And then this is a tetrahedral geometry when it comes to electron domain and molecular. Therefore, the bond angle must be 109.5 again. Okay. And lastly, we have this angle around nitrogen. We have 3 bonds around nitrogen. Therefore, we need to add a lone pair for nitrogen to have an octet of electrons. Now we know electron domain geometry of this nitrogen is tetrahedral, but only 3 of them are bonding. Therefore, this should be trigonal pyramidal molecular geometry, and the bond angle has to do with 109.5 degrees, but we know it because of lone pair is taking up more space, this bond angle will be a little bit less than 109.5. Okay, so these are our bond angles. That's it. This is the way. All right.